Hello, this is part A of homework 4 of process dynamics and control. What we're doing today is we're going to be assuming the viscous dampening in a manometer that can be expressed in terms of the pressure drop associated with laminar flow and fanning friction factor of 16 over the Reynolds number. Derive the transfer function relating the height difference between the fluid levels in a manometer to the pressure differential. So I have a mini drawing here of our manometer, and essentially what we're looking at is if we take our first height here and second height here, we want to look at the height difference, which is h. Next, what we're going to do is we're going to define our force balance. Let's go white. And essentially what we're going to be looking at is we'll see is our force will equal our gravity component plus our atmospheric pressure and our viscous pressures. And to pretty much expand the equation out, we're going to make this negative g times r, which is our gravity, times our density, times our area, times our height. And we're going to do negative g's because we're going to be defining our direction as down as positive. And then our atmospheric pressure is just our pressure times our area. And for our viscous pressure, we're going to have our delta P over our density, which equals 4 times our friction fanning factor, or fanning friction factor, times our length over diameter, times V squared average over 2. So then after expanding this out, what we'll get is 32 times L times our V squared average times mu, which is our viscosity, and that will be over D times rho times V times D. And we can see that we have some like terms that we can cross out. So what we'll end up with is delta P times 32 L times V average times mu over D squared. What we want to do is then we'll just multiply all of this by A. What we end up with is our rho for our viscous times A, which equals 8 pi times our mu, this times dH over dt. So now we can just plug this into our equation, 8 pi times mu over dH over dt. And our force balance equation will then be further expanded, where our F component is our rho times A times H, I believe so, over dt, which equals our negative G rho AH plus PA plus our 8 pi mu dH over dt. So now what we'll do is just divide over our rho AH, and what we end up with is d squared h over dt plus 8 pi mu over rho AH times dH over dt plus 1 over G times L, which equals, I believe, 1 over rho L times sorry, a little mistake right here. This is GH over L, and this is multiplied by P. Next, what we want to do is, since we are looking for a Laplace transform, we are going to convert this to that. So we're going to be left with s squared times big H plus, oh, and forgot to mention, to be able to do this Laplace transform, we're going to be simplifying our components down. So we're going to call this beta. This is going to be our gamma. And this is going to be our alpha. So what we're going to have is beta times S times H plus our gamma times H, which equals alpha times P. And to hash this out, our H will then be equal to alpha over S squared plus beta S plus gamma, all of that multiplied by P. And this is the equation we're going to be using in our code. And specifically, this right here is our transfer function. There we go. So for our coding part, I've already got our library set up and our variables plus our values that we need, which are given right here. So we're going to go ahead and start. So to begin, we're going to define what our area is, which is pi times d squared divided by 4. And then we're just going to define our alpha, beta, and gamma. So for our alpha, what we're going to have is 1 divided by rho times L, beta, which is pi times mu times over rho times area gamma, which is G over L. Then we're going to define our k value, which is just alpha divided by gamma, and then tau, which is 1 over np dot square root of gamma. So now what we're going to see is zeta, which equals our beta, divided by 2 times np dot square root of gamma. Oh, also, for beta, I added the um, G component, or gravity times pi times mu. And then we want to do our GP, which is going to be essentially our Laplace transform that we found. So if we do our tau squared plus 2 times zeta times, I believe, this will be multiplied by s squared multiplied by tau plus 1 . And then for our variables t and h, do sim gp lambda t colon of 5e3, and which equals 1000, and then dt, which is 0.1. And then I'm going to go ahead and fig dot add scatter and plot our chart. So it's equals t, y equals h. Okay, so small error. Fig equals make underscore subplots. Don't know why I forgot about that. And it's not supposed to be that. Be right back. Okay, the error is fixed. I just forgot to multiply something, the s by tau, but there we go. So what we see is we see our oscillations start very sporadic at the beginning, but then as our time moves on, our operation slowly starts approaching steady state, and around, I want to say around 30 seconds or so, maybe a little after, it reaches steady state. Now for the third part, if I could find my cursor, what we're going to have is we're going to be showing algebraically that the first two order systems in series will always have a dampening coefficient greater than 1 and thus overdamped. So to start and make this, we're going to start with our k1 over tau 1s plus 1 times k2 over tau 2s plus 1. And if we recall, our GP is k over tau 2s squared plus our 2 times zeta potential, or zeta times y s plus 1. Okay, so now what we're going to do is incorporate our transfer function into our GP equation. So GP will then equal k1 times k2 over tau 1 times tau 2 times s squared plus tau 1 plus tau 2 times s plus 1. I want to state that tau equals tau 1 times tau 2, and tau 1 plus tau 2 equals 2 zeta tau. So if we incorporate that, what we get is GP equals K1 times K2, where this is tau and this is 2 zeta tau. So tau s squared plus 2 zeta tau s plus 1. So simplifying this further, what we eventually get is tau 1 plus tau 2 over 2 squared greater than or equal to tau 1 times tau 2 squared. And this would eventually become tau 1 squared plus tau 1 times tau 2 plus tau 2 squared over 4 is greater than or equal to 4 tau 1 tau 2. And so now, simplifying this, what we get is tau 1 squared minus 2 tau 1 tau 2. By the way, this is multiplied by 2, I forgot that. Plus tau 2 squared, which is greater than or equal to 0. And this becomes tau 1 minus tau 2 squared is greater than or equal to 0. Thus showing our first order system will always be over damped. And now we're going to head to the last coding section. So for our next section, what I have is already set with our k, tau, and zeta values. And we're basically going to be using pretty much the exact same code here. So I'm just going to go ahead and copy this. Our GP is going to stay the same. However, we're looking to look at a little bit of a different thing right here, where our WN times T where our WN is equal to this is 1 over tau, and we'll put our mode as equal to lines, and this should, yep, so this is our graph. As you can see, our oscillations are not as sporadic as up here. They're a little bit more constant. However, it is controlled by this WN value. So if we make it so that we make half that value, we can see our oscillations start to come a little bit wider. However, if we go even further, we can see they get really wide. And the closer we get to 1, they start to go back to where they originally were. So 0.5 gives us a good balance in between, where we have a good amount of oscillations while having a steady flow, I would say. And that is the conclusion for part A.